that would be good for you.
How's everyone?
Oh,
How was the fight in the train?
that's good.
Good, right? Okay, so we will begin with week 3. I will quickly go through the last week because, as you all know, that in the last week the major thing that we have studied is Fourier series, and we explained that Fourier series is used to write any signal, any periodic signal in terms of sine and cosines, and that's why we said that sine and cosines are Legos, and we can take any periodic signal and then we can represent that signal in terms of this series. So how we did that, we said that the general form for a Fourier series is f of t. So if we have a signal and if you want to represent it, if for example we have a sine wave or any periodic signal, so that can be represented by a constant term which is a naught, then summation of cosines with a constant an, and then summation of infinite sines with a constant bn. So this was a general representation. So what is important here? These a naught, a and bn should come from the signal which we want to represent from the periodic signal. So that's why we said that a naught is equals to 1 by 2 pi minus pi to pi f theta d theta. Now this f theta is actually the signal that we want to study. And we also said that in the general form this was 1 by time period minus t by 2 to t by 2, but later on we said that since everything is in terms of sine and cosine, so it is better that for a periodic signal we keep the period as 2 pi. So and you might have seen that in the end when we were solving some questions, most of the terms was like cos n 2 pi, cos n pi, and it was easy to solve them. So it means that whenever we have a signal, that signal, we will represent that signal as f of omega t or f of theta. And if, for example, I take an example of square wave, so I can say it's, for example, 1 between minus pi. Okay, so if I take an example, instead I should write this example is, okay, so we have taken this example that if, for example, we have a triangular wave, and if this is pi and this is 2 pi. So it means that this is a periodic signal, this axis is omega t, not time axis, this is omega t axis, which is angle axis. So after 2 pi, the signal is repeating. So it means that now our signal f of theta is this one, and if we further simplified this signal as f of theta equals to, we written an equation for this one. I don't know what is the equation at the moment, but we said, okay, if for example this is 1 plus t, or simply t, we said that it is from 0 to theta to pi, and similarly for it's 0 between pi theta to 2 pi. So it means that this is a periodic signal. So the very first thing that is that whenever you get a periodic signal, so the very first thing is to get a function out of it, a mathematical function, and once you have a mathematical function, then you can use these equations to find a naught. So now this a naught is based on your function. Then you need to find an, which is f of theta cos of n theta. So in this case you have a cos with it. So here you have more complex integration. And then finally to find Vn, we need to write the same function in terms of sine n theta. And so it means that we are taking a function and then we are putting it in these constants, and finally we are taking these constants, merging them here, and this is how we represented a signal in terms of sine and cosine. So this signal was simply 1 plus t, or it was a t function, it was simply rising, but later on we converted it into sine and cosine. And we also said that for this we also draw a line spectrum. How we draw a line spectrum? So in this line spectrum, we draw it with respect to n. So you can see that n is starting from 0, which is a naught, 0 up to infinity. Now you can see that if, for example, a naught has some value, we will draw a certain line, whether it is positive or negative. Then we will go to 1. Now at 1, we have a1 and b1. So we have seen that for certain signals, a1 was 0, for some signals, b was existing, for some signal a. So imagine that here a and b both were having some value, so we will simply draw it. So we draw a line spectrum for this case. So this was a quick recap about Fourier series that we have already studied. But this Fourier series was called trigonometric Fourier series. Why it was called trigonometric Fourier series? Because we have trigonometric identities here, which is sine and cosine. They are trigonometric identities. Now we are moving towards exponential Fourier series. There is not much difference between if I say this is trigonometric Fourier series and if this is. So before I go into more detail about mathematics, so there are some key differences in trigonometric and exponential series. The very first difference is, as we said, that if we draw a line spectrum for a trigonometric series, so it will start from 0, 1, 2, 3, up to so on. If, I don't know, but if they have any number, any values, we're going to draw those values. So this is line spectrum for a trigonometric series. However, later on we will see that the difference between trigonometric and exponential is that in case of exponential, you have values on both sides. You have -1, you have +1, you have -2, you have +2, and so on. It means that trigonometric series can visualize both frequencies, negative frequencies as well as positive frequencies. So this is one of the key differences in this. There are other differences. We do have difference in the mathematical form. For example, we know that in this case a naught has some value, an has some value, and bn, which we already know, 1 by 2 pi minus pi to pi f of theta d theta. We just saw that these are the coefficients for Fourier series if it is a trigonometric Fourier series. However, if we go for a Fourier series, they have a different set of constants. So we represent constants for a trigonometric series as r. So they have r naught, which is same as a naught. R naught and a naught is same in both series. But the difference will come when we have Rn. So it means that in trigonometric Fourier series, we have a naught, which is DC level, we have an, we have bn. An and bn are like this. But in trigonometric, in exponential Fourier series, we don't have an, we don't have bn, we only have Rn. And let's well see that what is the formula for Rn and how we're going to derive it. Okay. Another important thing is, which we will see later as well. For this, we already know that these a naught, an, bn, they are real values. So if, for example, you finally calculate it, you will get it. For example, maybe an is 4 divided by n pi. So for example, if I put n equals to 1, so it would be 4 divided by pi. So it means that it is some real value. Right? It is some number. For example, 4 divided by pi would be 1 point something. So it means that this is some number. So the coefficient of trigonometric Fourier series, they are real numbers. They have some real value. However, in case of exponential Fourier series, Rn's are not real numbers. They are complex numbers. If you remember, I explained a little bit about complex number, that a complex number is a plus iota b. So they have this extra term, which is imaginary term. This is purely a mathematical tool basically. But if anything have this j term, it means that this term, this number is a complex number. So these are some of the key differences in exponential Fourier series. Later on we will see that how we're going to find Rn. We will see that in Rn you will get a J term. So, but these are some basic differences. So now we're going to start with. So now we're going to start with Fourier series. Trigonometric Fourier series, and you will see that to find a trigonometric Fourier series, okay, so now we're going to find trigonometric Fourier series, but we will start from Fourier series. Sorry, we're going to find exponential Fourier series, but we're going to start with the basic trigonometric Fourier series, and we will see that how we're going to convert. So we all know that Fourier series is f of t equals to a naught I need to get some tissue papers. Let me find some tissue papers.
I wonder who they got the tissues.
Yeah,
What is that? Bro, I expect from your boy to
I know. Something.
something's never changed. No, it doesn't reply. Doesn't it? Try.
Okay, so we know that it's a naught plus summation n equals to 1 up to infinity an cos of n omega t plus summation n equals to 1 up to infinity bn sine of n omega. This is, we know that this is a trigonometric Fourier series. Now we're going to convert this into exponential Fourier series. We all know that if I want to write cos of n theta in terms of exponential, we can use Euler identity. So as per Euler formula, if you have a cosine term, you take this and put it in terms of e power j n theta plus e power minus j and theta. This I explained in the very first lecture. So and sine theta is e power j n theta minus e power minus j n theta divided by 2, and we also have a j term in this case. So this comes from the Euler formula that if you want to express sine and cosine, we can express this in terms of exponential, which is e power j n theta plus e power minus j n theta divided by 2, and same goes for the sine, but in terms of sine, you can see that we have a negative sign here and we have a j term here. So the next step would be take those values and put them here. So it means that it would be a naught plus summation n equals to 1 up to infinity a n, and inside we need to put cos of n omega t. So now you have here n omega t, so it means that the whole term will go here as n omega t, right? So I can write it as e power j n omega t plus e power minus j n omega t divided by 2 plus summation n equals to 1 up to infinity bn, and we can put e power j n omega t minus e power minus j n omega t divided by 2j. So it means that I have done nothing. I have simply substituted these values inside. The next step is that I will just take this 2 outside because I want to play with these exponential functions. So it's a naught plus one by 2 a and outside it's g and omega t plus e power minus j and omega t. Similarly, here it would be infinity 2j on its side e power j n omega t minus e power minus j and omega t. My aim is actually here to combine terms which look alike. So you can see that here it's e power j n omega t and here it's e power n j n omega t. Similarly, in this case you have negative. So I want to combine them. And since limits are same, so it makes sense that I can easily manipulate them. So I can write it as a naught plus n equals to 1 up to infinity. So now let's see that. So it means that I have this term and same this will be multiplied here. So it means that if I want to take e power j n omega t from here, so e power j n omega t, if I want to combine these two terms, so take this term and then take this term. So it means that this e power j n omega t is common, which I have written as common. I also know that 1 by 2 is common between 2, so I can write it as 1 by 2. Now coming to next thing. So it means that here is an and here we have bn by j. So it would be an plus bn by j. So this was the first thing that we just separated. Now the second thing is n equals to 1 up to infinity. Again, what I'm trying to do here, e power minus j n omega t. I want to take this one out. So in this case, again, you can see that I have an here, right? And 1 by 2 is, I can take 1 by 2 common from both sides. It's 1 by 2. And here I have minus bn by j. So the only difference here and over there was that in one case we have this plus sign and the other case we have this minus sign. Okay, so normally what happens that we don't want j in the denominator. We want to bring it here. And same goes for here. So one option is that if I want to bring j on top, I can multiply and divide by j, which is simple mathematics, right? And here I can j divided by j square. And I know that what is the value for j square. I know that j is under root minus 1, so j square is simply minus 1. So I can substitute it as minus j. That means that if you have 1 by j, you don't need to do all this, you can simply write it as minus j. Okay, so now is equals to an plus summation n equals to 1 up to infinity 1 by 2. Inside it would be an minus jbn e power jn omega t plus summation n equals to 1 up to infinity 1 by 2, and here since there is already a minus, so it would become plus j bn e power minus j n omega t. It's clear so far, right?
Mm-hmm. Clear.
Okay, right. Now I want to simplify it further. So one thing I can do is somehow, if I make these two terms same, so I can somehow simplify it further. So what is a possible way to make e power minus j n omega t is e power j n omega t? What is a possible way? What I can do with only this thing? What I can do with this to make it look like this one? You know, we have control over n, so your n has some numbers. So what I can do with this n to make this minus s plus? What is a possible way? What I can substitute n as to make it
-1.
yes. So if for example we put n equals to minus n, if you assume that n is equals to minus n, it means that this thing would become a plus. We will see that this will not impact our equation. So if for example we know that in this whole equation is multiplied by e power minus j n. So if you are trying to play with this equation, if you are going to put n equals to minus n, we also need to put n equals to minus n, we also need to put n equals to minus n. So overall, there would be no significant impact. Okay. Now, replacing n by minus n in second term, so it would be an plus 1 by 2 so I will come to limits later on, but 1 by 2 here it is a minus n. This is not 2 minus 1, this is 2 subscript minus 1. Okay, so it's a in the subscript, it is minus n, plus j b in the subscript, it is. So now this becomes plus j n omega t. So now it means that things are getting better. So now I can combine these two terms, but we still have problem with the limits. Now what happens with the limits? So your actual limits was n equals to 1 up to n equals to infinity, right? So it means that now what we have done, we have substituted n equals to minus n. So it would be minus n equals to 1, and similarly this one would be minus n equals to minus infinity. Sorry, minus n equals to infinity. We can now again change them, multiply both sides with a minus. So this would become n equals to minus infinity, and this would become n equals to minus 1. So it means that by reversing n, we need to reverse the summation. Okay. So it means that here what we can put minus 1 to minus infinity, right? But normally what happens that if you remember, if you see this limit, we start from a lower number and we go to the higher. So in this case, even if we write minus 1 to minus infinity, or we write n equals to minus infinity to, it's the same thing. So it means that now we have two limits. We have n equals to 1 up to infinity, whereas the second limit is n equals to minus infinity to minus 1, or you can say n equals to minus 1 to minus infinity. It doesn't matter. Okay, so now what I can do is I can simplify this equation further. How? I can write it, so this was A now. I can simplify this equation further. How? I will write this whole equation as summation n equals to minus infinity to n equals to infinity Rn e power j n omega t. So this is final equation of trigonometric Fourier series. Now we will see that, because here we have just written that your f of t is equals to Rn e power j. So it means that we have, so this is common, e power j n omega t, e power j n omega t was common, so it's here. So it means that Rn, I have substituted these things for Rn. So it means that now we need to see that what is value for Rn. You can see that if I say n is between 1 to infinity, Rn would be having this value. If I say n is between minus 1 to minus infinity, Rn has this value. So it means that now I know what is the value for Rn, but I have more simplified version. Any questions so far? So it means that now I can say I need to find Rn. What is value for Rn, right? So I know if it's between 1 to infinity. 1 to infinity means if n is greater than 0, right? So if n is greater than 0, what is the value for Rn? If n is greater than 0, what would be the value for Rn?
Should be 1.
No, it's this value, right? It's this value, because if I see this equation separately, so if I only take n equals to 1 to infinity, this term would come here and the rest is same. So it means that Rn has value 1 by 2 an minus j bn. Similarly, if I want to see that what is the value for n less than 0. What is value for n less than 0? What if I put n less than 0? What would be the value for Rn from this equation? Yes, so from this equation I can see that if I have this limit, so I'm doing nothing, I have combined these two equations and now I'm trying to see it again by breaking it between two limits. So if the limit is between minus infinity to minus 1, which is n less than 0. N less than 0 means n is an integer, right? So n is an integer. So less than 0 means the first value that will come is minus 1. And then it will go up to infinity. So it means that I know this value is 1 by 2. A minus n plus j b minus n. So it means that now I have this value, which I have value for n greater than 0, I have value for n less than 0. Is there anything missing in this Rn? Because you can see that here the value is from 1 to infinity and here the value is from minus infinity to minus 1. Is anything missing in n? What is missing? 0 is missing, right? So, what happens with the 0? As I said previously that your Rn, which is, if I say R naught, is same as A naught. So, for n equal to 0, your R naught is same as A naught. And later we will see again, we will come to their formulas as well. Okay. Now, what I want to do, I want to somehow, that when we want to write Fourier series, so I know the formula for A naught, I know the formula for An, I know the formula for Bn. So same I want to do that, I get some formula for Rn, because at the moment it doesn't look any formula, right? Because I don't know A and Bn. So what I can do to write a formula for this? What could be the possible step in this to derive a formula? What do you think? We started this derivation from a Fourier series, right? So at every point we are taking the original Fourier series. So it means that these An and Bn, they are same as Fourier series at the moment. So the most logical step here would be to substitute these An and Bn here and try to see that what is happening, because I want to find the formula for Rn. So let's say here we have two cases, right? So let's take the first case. So I want to find Rn for n greater than 0. What is formula for An? How we write An? So 1 over pi f of theta cosine of n theta d theta, and what is Bn? 1 by pi f of theta d theta, and we know these limits as minus pi to pi. Yes, right? So it means that we know these values, we can substitute them here, and we will see that we will get to some point. So if I substitute these values here, so it would be Rn equals to, I know there is 1 by 2 pi outside, I can keep it outside, right? And similarly we have 1 by pi here. So it would be 1 divided by 2 pi. So this is something which will come as outside. Inside now I can simply put An minus j times this one. So it would be An is f of theta cosine of n theta minus j. What is Bn? Bn is f of theta sine of n theta d theta. Sorry, I will d theta here. So it means that I have simply substituted these values, but I can see there is something common. What is common in here? You can see that this integral, this theta, this d theta, similarly integral theta and this d theta. These are common in both sides, right? And I also know that in both cases the limit goes from minus pi to pi, so we don't have any limit with any problem with the limit as well. So it means that in this I can take these things common. So let's do that. So it would be 1 by 2 pi. Inside it would be minus pi to pi f of theta d theta, and inside it would be cosine of n theta minus j sine of n theta. Okay, so finally, if I move further, if I put it as 1 by pi, I write it as minus pi to pi f of theta d theta, and here cosine of n theta minus j sine n theta. Or I don't need to do this split here. Okay. Does this looks familiar? Can I get something from this? So if we see e power jx, this would be cosine of x minus j sine of x. This is identity for cosine. This actually comes from if we combine these two together, we will get this one. So it means that this cosine n theta minus j sine n theta is actually e power minus j n theta. I can put it as like this. So finally the equation would turn out as 1 by 2 pi minus pi to pi f of theta e power minus j n theta d. And this equation we found for n greater than 0. So it means that we can find Rn with this formula. So if we know function, value of function, and if you multiply it with exponential and take theta, we can find Rn. So if we somehow equate it with the an, so in case of an, what we were doing, we were taking f of theta and we were trying to multiply it with a cosine of n theta, but here the difference is that you are multiplying it with exponential. Okay. Can you do the same steps for the second part, which is Rn for n less than equals less than 0? Can you do these steps one I done for the other part?
Okay.
Probably. Let's see. If you want the white one.
So you need to find Rn, which is a 1 by 2 a minus n minus j b minus n. I guess here it's plus. Yes, so now again you know what is formula for an. We already know formula for an. Similarly, you know formula for bn. But the only difference here would be you know formula for an, right? But here you have a minus n. So there is no difference. Just replace in the formula of n, just replace n with minus n. So you can see here minus n will come here, minus n will come here, and that's it. There is no difference in this equation and the other equation. The only difference is this equation is for an, right? This equation we know is for an. So what would be equation for a minus n? So for a minus n, just replace this n with minus n, replace this n with minus n, and you will get equation for a minus n. And same you have to do for bn. And then tell me that what you get for as your answer. Any help in getting to find the answer? You know that if there is a minus sign inside cos, it doesn't affect, right? It stays as cos. And if we have a minus sign inside sine, so we can write sine of minus theta equals to minus sine of theta. We can take minus outside, so it will come here. So it means that these two equations look same. You can see this was equation which was for a n. So you can see f of theta cos of n theta d theta minus f of theta sin theta. If I see this equation, this is f of theta cos of n theta minus j. So both equations are same. So it means that I don't need two different formulas to find Rn. I can use same formula for both of them. So the only difference is just solve it, and then finally you can put it n minus 1 to minus infinity and 1 to infinity. So it means that we need only one formula for Rn, and that's why, if you remember, when I was when I written the final form for this was f of t equals to summation minus infinity to infinity Rn e power j and omega t. So this is your final form for exponential Fourier series which you just saw. So it means that here Rn can be found using this formula, and this formula hold for both n greater than 0 and less than 0. So it means that Rn is same formula can be used for finding both. Again, there is something missing, right? There is n equals to 0 is missing because we don't have n equals to 0 in this formula. But we can say that this formula, we can use this formula to find a naught as well. Normally what happens that you first calculate the formula and then put n values, right? Same holds for this. But if I put n equals to 0 before doing any calculation, if I put n equals to 0, so this will give me r naught equals to 1 by 2 pi f of theta e power 0 d theta, and I know that e power 0 is 1. So it means that r naught is same as a naught, which was for a Fourier series. So that's why we don't need an extra formula. So it means that r naught will be calculated with the same formula that we done for a naught, whereas Rn will be calculated with this formula. So the DC value would remain the same both in either this Fourier series or either trigonometric Fourier series or exponential Fourier series, whereas the only thing that would change is the value of Rn. And now you can see in the beginning of class I told that Rn is a complex number, and you can see that clearly you have j. So even if I take integral of j, it means e power something, it will remain e power the same thing. So this Rn is a complex. Any questions so far? So it means that we just went through this derivation so that you know that how we're going to find it. I could have written the formulas, but it's better that you know how we move from the Fourier series, just taking the help of Euler identity, put it in the formula, then come up with something where we generalize Rn with these things, and then finally I use the formula for An, Bn to get to this point, and similarly I use formula for An with n equals to minus n, and finally came to know that I have same equation. These two equations are same. So if I solve the equation, I will get to the same formula. So it means that the final formula for Rn is this one, and for finding A naught, we use the same formula as we have done in the Fourier series, which is just taking the average of a signal. And again, remember that we are dealing with Fourier series. So Fourier series is only valid for periodic signals. Well, let us see also Fourier transform, hopefully today. Have anyone studied these Fourier series and before?
Oh.
Right, so this was the same derivation which I have just done. This is just for your reference. Later on, we have used this Fourier, then we came splitting by putting the Euler identities. Euler identities are here, and then finally we came up with this formula. Then the next thing was to find Rn. So we said that Rn has two values. So we move further and we put for less than 0, for greater than 0, and we came to know that both have same equation, and then finally we generalize this equation as Rn equals to 1 by 2 pi, here it's 1 by 2 pi, minus pi to pi f of theta e power minus j n theta, and once I have the Rn, I can use this equation, which is the main basic equation for exponential Fourier series, and I can get the exponential representation of Fourier series. So now let's move towards an example, so that we understand what we have studied. Okay, so here we have okay, so here we want to find Fourier series for exponential Fourier series for a rectangular wave.
You know, only after you answer the question, you have to draw also the wave.
You can draw the line spectrum. I don't think that from the final Fourier series
Yeah.
you can draw the waveform, because it is difficult. We will do a lab workshop today to plot them with MATLAB. But yes, you will be drawing those spectrums, just the values for the magnitudes, but not the final represented waveform. So we have so this is pi k, and this is minus pi k. this maximum value is 1, and this is repeating on left and right. Just like. Okay. So what is the period for this waveform? What is the time period for this waveform?
0. Is it by the sun? It starts from.
If, for example, I take this point, you can see this is half, both sides is half. So if I start from this point again repeats at this, right? So 2 pi. It makes sense because at the moment we are going through the periodic signals. Okay. Now to find a exponential Fourier series, what we need to find? We need to find R naught and we need to find Rn. So we need to find R naught and we need to find Rn. Who will find R naught? Before finding R naught, just quickly write function on your notebooks. The very first step is to write function, right? To write f of omega t. Very first step is this one, and this axis is basically omega t axis, and this is So what is the value of a function? So we can easily see that the function has value 1 and it has value 0. So you can see that it has value 1 from minus pi by k to pi by k. What I should put limits here, where the function has one value. Where the function has one value. This point is minus. So you can see clearly the function has one value only in this period, right? So it means that I have omega t less than minus greater than minus pi by k to pi by k. It has some value, whereas between this and between this it has 0 value. And overall I can see that minus pi to pi is the period, which is 2 pi overall. So it means that else I can say minus pi greater than less than minus pi by k, or this is 0. Right? So it means that it has value only here, whereas at this portion it's 0. And to find Rn, what we do? So we have Rn, which is 1 pi, 2 pi minus pi to pi f of theta e power j minus j n theta. So it means that I need to split this integral. So it would be 1 by 2 pi. It would be minus pi by k, 2 pi by k. F of theta is 1 in this time. E power minus j n theta d theta. And I know for other two cases, the integral would be 0 because the function has 0 value, right? So that's why instead of writing function here, I just put 0. So ultimately it would be 0 for this case, and for the for the last case it is also 0. So it means that the function has value only for a small interval. Right. So it means that I can further solve it 1 by 2 pi. It would be minus pi by k to pi by k e power minus j n theta d theta. So I have simple integral to solve, which is an exponential function. So what would be the integral for exponential? It would be 1 by 2 pi. What I should write here? It would be minus j n theta, and in the denominator it would be j n. Right? So integral is with respect to theta. So if I take integral, it would be e power minus j n theta. And then if I again take the derivative, it would be minus j n, and it would go to this denominator. And I know that the limits are minus pi by k to pi by k. I will further solve it here. So Rn equals to 1 by 2 pi. So I know that this term, there is no limit, so I can take outside 2 pi jn, and inside I can apply limits. So upper limit will go to theta, and then the lower limit will go to theta, e power minus j n, and in the place of theta I can write pi divided by k. Similarly, minus lower limit e power minus j n, and since there is another minus, so this minus will become plus. So at the moment I will just write it like this so as not to confuse. So it would be minus 2 jn, and inside it would be e power by k minus e power j n pi by k. Any confusion so far? So I've simply substituted the limits, and finally I have this value. So when you will be solving exponential functions, exponential series, so you will see that in the end you will get some exponential terms. One of them is minus, one of them is plus. So whenever you have some scenario, you will straight away think about representing these functions in terms of sine or cosine. If I multiply, if I do it further like pi n inside, if I should write, if I multiply minus inside, so it would be e power j n pi by k minus e power minus j n pi by k. And I also, if I also take 2 j inside, does it looks familiar? Because this is similar to what we represent a sine. So sine, if we write it in terms of Euler, it would be sine of j theta minus e power minus j theta divided by 2j. This is Euler, right? This comes from Euler formula. So it means that we can easily present this with an Euler function. So it means that Rn would be equals to 1 by pi n, and as per Euler, e power j theta minus e power minus j theta, or if I would write x, not to confuse you, x divided by 2j is equal to sine of x. So it means that whatever is here with sine would become the angle of whatever is here with exponential would become the angle of sine. So I can write it as sine of n pi by k. So it would be n pi by k. So it means that now we have simplified it in terms of a sine wave. Any confusion so far? Okay. You remember we studied in the very beginning that if we have sine x by x form, this is called sinc function in the very first class. And if we roughly draw a sinc function, it looks like this. So it goes like it starts its peak here and then go like this. So we can, looking at this, we can represent it in terms of sinc function. How? So what happens with the sinc function? So sinc of x means sine x by x. So whatever is here will come in the denominator. So it means that to make this sinc, the same thing should come in the denominator, right? So if I further write it, it would be sine of n pi by k divided by n pi. So it means that I have n pi, but I'm still lagging with this k term. If I have the k term, I can convert it into sinc. So what I can do is I can multiply k here and I can divide k here. It will not change, it will not affect the equation, right? Ultimately it will be 1. So out of this, now you can see that this term would become a sinc function. So I can write it as 1 by k would come out, and here it would be sinc of n pi by k. So it means that it is a sinc function. So this means that the coefficient would look like a sinc function. As we know that the coefficients are not continuous. So it means, if we want to, as we discussed previously, that in case of exponential, you have here, then you have here, and same, you have spikes at different points. So 0, 1, 2, this is -1, -2. So looking at this Rn, which is a sinc function, so it means that this is not a continuous sinc function. Why? Because you put n equals to 1, then it will give you a value and so on. So it means that the lines, the spectrum of the coefficients will look like the spectrum of the coefficient will look like a sinc function. So you can see from this we came to know that Rn is somehow sinc function. So you can see if you put Rn n equals to 1, you can put k something. So this one is plotted for k equals to 4. So you can put k equals to 4, and here it will be 4. So 1 by 4 sinc of 1 pi by 4. So if we can directly solve sinc function as well by using some calculator or something, but normally sine is easy to solve. So if we look from this equation, so you can put n equals to 1, n equals to 1, k equals to 4, you will get one single number. Then you put n equals to 2, you will get another single number. So this is drawn with respect to n. So you can see that you have spike, but if we overall draw a rough sketch over these spikes, you will see that they look like a sinc function. So it means that the coefficients are a sinc function. Now, You can see here I have written in the place of 0, which is a constant term, it's 1 by k. So can somebody find the R naught in this case? You know the formula for R naught, right? Because we just calculated Rn, which wasn't R naught, which was not including n equals to 0. So can someone please find R naught? Find R naught. Formula for R naught is same as A naught.
I need to replace it. Keep divided by k. Come on. Just replace 0. It's p negative button.
Find the value for R naught. This would be the formula for R naught, right? Because function exists only between these two limits, it has a value of 1, and there is no exponential term in this case, because this is simple R naught. If you solve it, you will finally get it as 1 by k. So it would be 1 by 2 pi, inside it would be theta minus pi by k to pi by k, 1 by 2 pi, upper limit pi by k, lower limit is another minus here, so it would be plus pi by k, 1 by 2 pi, and here it would be 2 pi by k. So it would be 1 by k. I know this is boring, but this is what it is.
Let's try to comprehend it.
Yeah. Did you get 1 by k?
Why is it not 1 over 2k?
What? Sorry?
Why is it not 1 over 2k?
Because you have.
Yeah, when you have k plus k.
So you, no, so k would go in the denominator as an LCM, so k would be common,
Just
and then
take
pi
it.
would be 2 pi,
Hmm?
You
right?
have this result. If you replace
Okay.
with
yeah.
0,
Yeah, yeah, yeah.
sync of p
So k
divided
would
by
be
k,
LCM.
that means it's equal tends to the 1. It will be the same result.
Yes,
Probably.
maybe.
Maybe
Hmm.
because we get 1 divided by k after we did the formula. So maybe the sync it's the limit 1. The limit is 1.
I'm trying to see what this is.
As I said, it's very important to draw these once you have something, so you have to draw then these numbers, which you have already done for the previous case. This is another example that is for the rectangular wave. but this is a bit more simple. I will not solve it here. Probably sometime tutorials. So this is an easy version of what we have seen. But we will not be solving this. We will move towards another important concept, which is called Fourier transform. I know that these things are so rigorous that you will be finding them overwhelming. But don't worry about it. Do practice these questions and try to understand it. But don't worry about too much about exam. We'll see. Yeah. But I know this is very rigorous and very comprehensive. But try to solve.
The time was is so short.
Yeah. So try to solve these examples that I do in the class. Try to get your hands on integration, derivation.
Yeah, I'm writing.
Okay, so now moving towards another important concept, which is called Fourier transform. So far we have studied Fourier series, which was trigonometric Fourier series, and then we went to exponential Fourier series. But Fourier series is essentially for a periodic signal. So it means that if you have a non-periodic signal, Fourier series will not hold. So that's why we say that Fourier series is only limited to periodic signals. But what if we have an aperiodic signal? We still want to analyze that signal. So to analyze non-periodic signals, we have Fourier transform. And why it is important to learn Fourier transform in terms of physical interpretation? If, for example, I'm speaking with certain frequency, each time my amplitude of my voice is changing as well as frequency is changing. There are some frequencies which are audible frequencies which we can hear, 20K or something. So it means that there are also some frequencies which we cannot hear. But in order to analyze those frequencies, we need some tools. So there are some effects. For example, current is flowing in the wires, but you cannot hear any sound or anything. Why? Because the frequency is not audible. So in order to analyze a signal for what kind of frequencies are inside, we need Fourier transform. So for example, you have a signal which is coming in, and in terms of signal processing. So you know, for example, that human voice has this certain range of frequency, whereas noise has this certain range of frequency. So if you get certain signal, and if you want to remove that noise, so you can simply transform that into frequencies, then take those frequencies out, and then you will come up with a clean voice. So that's why, in terms of physical interpretation, Fourier transform is very important. Also for those who are from power system, so what happens in power system is that we deal with sinusoidal signals. We deal with AC signal that is actually coming from our socket. And most of devices, they are designed for a single frequency, which is 50 Hertz, or in some countries it is 60 Hertz. But what happens that because of so many load connected in the power system, for example, we have motors, we have generators, we have heaters, and so many things. Because of that, noise generates in the power system, and instead of only 50 Hertz, you have many other frequencies in the signal, which are called harmonics, which are undesirable. So now again, if someone gives you two AC supplies, and if he wants to ask you which one is better, so looking at them, we cannot judge it. But once we do the Fourier analysis of its output, we will see, oh, okay, this supply is giving me 50 Hertz, but also giving me, let's say, 100 Hertz and 150. So there are many other frequencies. So I will clearly say, okay, no, this is not good because it is not giving me a fixed frequency. How I'm going to know that? Using Fourier transform. Normally, in power system, there is a thing called total harmonic distortion. So normally for every manufacturer, they define a certain limit. For example, 5% or something. So to get those numbers out of any signal, we first need to know what are different frequency components. Once we know the frequency component, we will see later from Fourier transform, we can also get to know what is the magnitude of each component. So once, for example, I have a system in which I was having 50 hertz, 100, 150, and so on. And someone asked me that I only need 50 hertz. Design an equipment which gives me 50 hertz. So I will apply Fourier series. I will see, okay, at 50 hertz I have 10 volt. At 100 hertz I have 5 volt. At this I have 2 volt. So this is terrible power supply. Why? Because I need the whole in the fundamental frequency, but I have many other frequencies. So to analyze such systems for various kind of frequency, it is very important that we know how to do that. And to do that, we use Fourier transform. Okay. First thing is Fourier transform is for aperiodic signals or non-periodic signals, and this is quite easy. If you want to find a Fourier transform, we just need to take the signal. We need to multiply it with e power minus j omega t, and we need to integrate between minus infinity to plus infinity. There is no pi to minus pi. So in case of Fourier transform, since the signal is not periodic, so it means that the signal can be up to infinity. So we don't know where the signal is ending. So that's why we write it as that if the signal is continuous in both sides, minus infinity to infinity, we just need to integrate it by multiplying it with exponential. So it means that if I am going to do this integration, I will get a frequency domain analysis. Another important thing is that your input would be continuous, and you can see that the output would also be continuous. So it means that same signal in time domain, I want to see it in frequency domain. And sometimes it is useful, you cannot see something in time domain, but you can see it in frequency domain. Same goes for the other way around. If I have a Fourier transform and I want to convert it back to the time domain, so I have to use two things. You can see here it's minus, so here it would be plus. And the second thing is, we would be having 1 by 2 pi here. So these are the two differences which we have Fourier transform, and then if we take inverse Fourier transform. So for this we will straight jump to the example, because these are just formulas. I will not go into any derivation. So in this case, you can see that one important thing, the function, the x-axis is time. Because in the previous case, we intentionally made our system omega t, so that why? Because everything was sine, cosine, and we knew that the period is 2 pi, it is periodic. So that's why we put this axis as omega t, but now this axis is time. So it means that now we don't know the period because this is not periodic. So this is the signal. Is it periodic? Is it a periodic signal?
No.
No. Why? Because this is not happening again anywhere. All of the other signals previously were periodic. So it means that in order to find Fourier transform, what I need minus infinity to infinity. This is demand from the integration, right? So I need to go to minus infinity to infinity. But here the signal is between only these 2 points. So it means that from this to minus infinity, the signal is 0. From this to infinity, the signal is 0. So it means that the effective limit for the this example would be tau by 2 minus tau by 2 and tau by 2. Okay, so let's start. So we know that just before that, if you have signal f of t, if someone asks you to find the Fourier, so Fourier is generally represented by g of omega, or sometimes
Tangent.
you can also represent it by f of omega. Just remember that in time domain, to make a difference between the two, the t is changed with the frequency, because now we are in the frequency domain. The second thing is, if this is small f, this side, the variable is normally used as capital G, capital F, capital H, so as to differentiate. Okay,
It's not
so now it means that G of W is equals to, there is no 1 by something, so minus infinity to plus infinity f of t e power minus j omega t dt, right? Then I know these are between minus tau by 2 and value is a e power minus j omega t.
So what's tau again?
This is just a number.
Oh.
Just a number. Normally when we do examples from the beginning, we keep things general. So maybe this is 1. So it would be minus 1 by 2 to plus 1 by 2. So mostly in exam or in your tests, you get numbers, because dealing with numbers is more easy than dealing with the variables. For example, instead of a, you will see it as 1 or 2 something. Instead of tau, you will get some number. So this is just a number, but we want to keep it general for just for the sake of solving. So this is Fourier transform. So you can see that this is a rectangular wave, right? So this is Fourier transform for aperiodic rectangular wave. We previously seen where rectangular wave was repeating, but in this case it is not. So as a rule of thumb, we take constants outside. This tau is not period, okay? So minus j omega t dt. Now you can see that the limit in this case, here you can also see that it's dt. In all previous cases it was d theta and so on. So here it's dt. And also here you have minus j omega t. Now I can solve it easily, right? It's just integration for an exponential function. So it would be a e power minus j omega t. In the denominator it would be minus j omega, and limit will go from correct so far, right? So the next step is to apply limits. Before applying limits, we just need to take these constants outside, and inside the limit will go to t. So it would be upper limit minus j omega tau by 2, and then we have the lower limit minus, and in the lower limit this minus would be cancelled with this one, so it would be j omega tau by 2. You see, as I said, whenever you are dealing with exponential Fourier series, or now in case of Fourier, you can see that the formula is more or less same as of exponential series. It's just that we are not going for any pi and any period. So in the end, you will come up with something like this, and you will see that it turns out to be a sine or cosine function. So here I can see if I take minus out or if I multiply minus inside, so it would be a divided by j omega e power j omega tau by 2 minus e power minus j omega tau by 2. So it means that this is somehow close to what we want, but still to get the sine out of it, what we need divided by 2j. And why I thought to convert it to sine and not cos?
Minus.
Yeah, because of this minus. Very good. So because of this minus, I can clearly know that this cannot be converted into cos. So that's why I look for. So if I take this j inside here, I still need 2, right? So I can multiply and divide by 2. So multiply and divide by 2. And this division will go here. So it would be 2j. So ultimately, it would be g of omega equals to 2a by omega sine of omega tau by t. Correct? So this from Euler, and if we simply converted it into sine of omega tau. Now again you can see that this is going somewhere close to sinc function, right? I have omega t omega tau by 2. I can somehow bring it to sinc function. So let's do that. 2a. So I have sine omega tau by 2 divided by omega. So it means that I'm short with tau by 2. So it means that I can simply multiply and divide by tau by 2, right? So what I can do is 2a tau by 2 multiply, and then the same thing I have divided, and sine of omega tau by 2 by omega. So it means that this tau by 2 can come close to here, tau by 2. So it means that now this looks like a sinc function. And this can cancel with this. So the final function is a tau sinc of omega tau by 2. So I can write this as a tau sinc of omega tau by 2. So I know sinc of omega tau by 2 is sine of omega, the same thing, divided by the same thing. So it means that the Fourier transform for this case is a sinc function. And as I said previously that here your Fourier transform is a continuous thing. So based on value of frequency, any frequency you can choose and it will give you a continuous function. Okay, let's see it's any question on this? It's just solving integrals back to back.
No.
So it means that Fourier transform of a rectangular segment is a sinc function. We can try different values of. So, okay. So as your question.
I have a question. So you took a square or rectangular pulse and you turned it into a sine sort of wave. Why?
Yes. So here there are two differences. In case of Fourier series and exponential Fourier series, we were representing a signal with sines and cosines. So if you remember, when we were trying to draw them, so they were, for example, if it was a square wave, so you were seeing there were sort of spikes, but still the wave was close to that. But in this case, we are not representing the same signal with same in time domain. No, what we are doing, we are converting a signal into frequency domain. So these are two things. So in case of series, you are writing one time domain signal into another time domain signal, which is sines and cosines, right? So writing one time domain function into another function which is still time domain but sines and cosines. But in this case, you are transforming one signal into frequency domain so as to see how this signal looks like in the frequency domain. So that's why this is not representation. This is in time domain, this is in frequency domain. We will do today our lab for Fourier series, where you will be plotting Fourier for example, rectangular wave and different wave. You will see that they are not very close to, but close to rectangular
Is it
wave.
lab 2 or lab 1?
Sorry.
Or lab 1 or lab 2?
So today we are going to do lab 2 and a portion of lab 1 which was pending last time.
Yeah.
Right? Okay. So it means that a rectangular wave, which we see it in a time domain. So from here we were unable to tell what frequencies are in here, right? But when we converted it into frequency domain, now what we can do? We can put different values here and plot it. We will do it today as well. Not this one, the other one. So if we put omega equals to 0, so sinc of 0, this is an identity, there is a proof for that, but sinc of 0 is 1. Sine of 0 is 0. We know that sine of 0 is 0, right? But if you have sine of 0 by 0, this is 1. This is mathematical identity. So it means that sinc of 0 is 1. So that's why you can see that at 0, you have maximum value. And that maximum value, you asked a question, what is tau? So now we can choose different tau. So you can see that here it is plotted for 0.5 and A is 5. So based on that, you will get your value as 5.
It's one division by 0
Yes.
is possible.
And
Set by 0 by 0.
so on. You can see that now we can see it in frequency. So we can tell, okay, if a wave is a square wave, if for example, you have an equipment which is generating a square wave, it means that it is indirectly generating so much frequencies. You can see it has maximum value at 0 frequency, mean DC value, whereas it has small values on the other side. So from here you can judge whether it is good from equipment or not. So if for example you want to run a DC device with this, so more or less this is fine, but you can see that you have many other frequencies. So ideally you can see this Fourier transform is used to analyze the signal, how it looks like in the frequency domain. This is another example. I will leave it for tutorials. I will quickly cover some of important things for Fourier transform. Okay, so there are some well-known functions in signal processing, or you see it in your daily life that you want that are important to see what is Fourier transform for those. For example, we have an impulse signal. Impulse signal by its name it means that something happening for a very short time and huge. So you can see that in this case, the width of the pulse is almost 0. And at this point, your value of the function is infinite. Infinite practically means maybe some number, but we define an impulse function, or sometimes it is also called Dirac delta function. This term is delta. So unit impulse function or Dirac delta function. So this function explains that at t not equal to 0, anything other than 0, this function is 0. At t equals to 0, it's infinite. So it means that if we want to find, for example, area, so you can see that there is no width, there is nothing. If for example, I draw it like this, there is certain width and there is certain height, so I can find area equals to width into height, right? But in this case, you can see that the width is almost 0, there is nothing. So it means that in this case, I have 0 and value of the function in top is infinite. So 0 multiplied by infinite is something undefined. Meaning in mathematics, if we are multiplying an undefined thing, infinite thing with a 0, it's undefined. So we cannot define it. But for this special case, we say that this area, although in practical this is not the case. For example, what can be an example? If for example we have a long, huge building, so that building is there at certain point and it has huge height. So such kind of things are represented with an impulse. Or we can take an example for pandemic. You can see that it hit for a short time, but it was huge. So such functions are called impulse function. So we cannot define it, right? So but in practice they have something. So in mathematics, such area is defined as 1. So what we say that if we want to integrate delta function, which means to find area, this would be equal to 1. This is a mathematical identity in this case. So it means that if we have a function which is Dirac delta function, is 0 at t equals to 0, and at t equals 0 it's infinite, at all other places 0. Now we want to find Fourier for this. But to find Fourier, what we have in Fourier, if you want to find g of w, it would be delta of t e power minus j omega t d, right? So if I go a little bit in the previous case, you can see that this was a rectangular waveform, right? So you can see that if this is a rectangular form, you have certain width. If you keep on reducing the width, you will see that this will keep on extending. Why we have tau was not set to certain number. If for example you see in the lab by putting different tau, you will see that as you will reduce the width of this signal would expand. So where I'm going from here is, if I keep on reducing the width, this signal would keep on expanding. And if I reduce the width almost to 0, this signal would be a straight line. So indirectly we cannot directly find a Fourier transform from this. Why? Again, the problem is that if we say minus infinity to infinity, technically this signal is not from minus infinity to infinity. I would say this is 0 minus to 0 plus. I mean, it was at 0, but still it is a huge number, right? So it means that I can put t equals to 0. So I can do delta of t, and if I put e power 0 dt, so it would be 1. Now the problem is that, again, what would be the problem? The problem would be the value of function at this point is infinite. So that's why we say that from this we cannot directly infer the Fourier transform, but one important thing is that we can say that because we have seen that for a rectangular waveform, if we reduce the pulse width, the signal will expand. So that's why we say that for a Dirac delta function, the Fourier transform is always 1. And another important thing is that if you want to integrate a Dirac delta function from minus infinity to infinity, just integrate it, you will get it as 1. So from here we come to this conclusion because we put e power equals to 0, and if we still integrate it, we get infinite number. But we said that technically this is not infinite, but we define it with 1. So this is considered as an identity that if you integrate the Dirac delta function from minus infinity to infinity, you will get it as 1. And at the same time, if you want to find Fourier transform would be a straight line of 1, and always try to compare it with the rectangular function with width, and we see that as we reduce, it will be a straight line. Just last thing, and then we are finished. Just in the continuation.
Force. One last thing.
Okay, so
Give us some.
as I said, the important thing I want to show you is Dirac delta integration, minus infinity to infinity. We already know that if Fourier is 1 in frequency domain, but here I just want to show you integration of Dirac delta function, which is in time, which is not a Fourier series, just an integration. So as I said, if I go here, Dirac delta function is 0 if t less than 0. Clearly it is 0. So it means that this is 0 if t less than 0. However, as we said that if we, after this point, as soon as t is 0 or slightly greater than 0, this stays at 1. So it means that, and then again go to 0. So it means that for t greater than 0, this integration would be 1, because as we said that we equate it to 1. So for t greater than 0, it's 1. Do you know this function? Have you ever heard about unit step function? No. Okay, no problem. So unit step function is like this, which is 0 for t less than 0, but as t is greater than 0, it stays 1. Consider turning on a button for light. It was 0 before, but when I turned it on, the light stayed on. For example, I turned on my mobile phone, so all these things are unit step function. So it means that if I integrate a unit step function, sorry, if I integrate a Dirac delta function, this gives me a unit step function. So it means that integration of Dirac delta function is unit step function. And this function is, you will see a lot in engineering, everywhere about this unit, because at every place, any place you want to turn on something, that is a unit step. Before that, it was 0. So from this, we learned two key points. One was that the Fourier transform for a Dirac delta function is 1. This means that over the frequency it's 1. But if we want to simply find an integration for Dirac delta function from minus infinity to infinity, it would be a unit step function, because it is 0 for less than 0 and 1 for greater than 0. And later we will see that we will be using them a lot. Any question on this? This was slightly trickier. I mean, from directly looking at the output, it seems easy, but understanding it is slightly confusing, because we, at some places we say, okay, this is it. This is, if mathematics say yes, so it is yes. So just consider these two things in your mind. Any question on this?
How do we use, say, Fourier transform for noise analysis?
Noise analysis. So what you're going to do, you have to consider that noise signal and represent it in the form of a function. And once you have a function for that, then you follow the same step that we have done in the previous case, and you come up with a frequency domain signal. So if you remember in the previous case, So consider that this was a noise signal, just for the sake of understanding. So this is a noise signal, so we come up with a final frequency domain signal. And when we plotted this frequency domain signal, now I can see that what are frequencies, what are their magnitudes. So now you can see at 0, I have 10 magnitudes. At minus 10 hertz, I have this at 10 hertz. So from here I can see that what are different frequencies in that noise signal.